Thank you everyone for coming. This is MPark.patterns, pattern matching in C++. This is going to be a talk about a library that I wrote in C++ 17 to try to support pattern matching. We'll go through a lot of the intricacies of it today. So my name is Michael Park, perhaps better known as MPark in the community. I'm currently a software engineer at a company called Mesosphere, where I'm building out the visions to see what it would look like to have an operating system in the data center. I'm also a member of the C++ Standards Committee, and I'm also the author of the standard variant implementation for libc++. So to set the stage for the talk, I'm going to cover a brief history of how pattern matching has gone through history over time in different programming languages. So pattern matching started all the way back in 1960s, originally with Snowball. And it provided a language level support for pattern matching on strings. Now, Snowball was a text and symbol-based programming language, and so this made a lot of sense for them. In 1987, Perl came along and evolved that idea, and they basically introduced by far the most popular and well-known, well-understood form of pattern matching today, and we all know that technique as regular expressions. So ML took that idea of pattern matching on strings and generalized it to more complex data types like tuples and variants. In the 1990s, Haskell and OCaml were introduced with pattern matching support. I lost my cursor here. There we go. Sorry. So yeah, Haskell and OCaml were introduced with pattern matching support. And in fact, it's actually at the very core of most functional programming languages. And more recently, many mainstream languages have also adopted the feature. The most popular ones from my perspective are Scala, Rust, and Swift. But other languages like C#, Java have also picked up pattern matching as well. And for C++, there's been two efforts that I know of towards introducing pattern matching. The first one is a paper called Open Pattern Matching for C++ by Yuri, Gabby, and Bjarne, which was published in 2013, and it shipped with a library solution called Mach 7, which involved a lot of macros. In 2015, 2 years ago at this conference, John Bandelag introduced Simple Match, which was a C++ 14 library solution with no macros. And that's about it. So 35 years into C++, almost 35 years, we still don't have the full extent of what pattern matching gives us at our disposal. So I have a question, which is, what is the most common answer to this question? Why doesn't C++ have feature X? Most common answer. Michael?
No one's proposed it.
No one proposed it. OK, so we need a standards proposal, some kind of proposal to actually add it to the language. So in 2016, David Sankel wrote a standards proposal to introduce pattern matching, and this paper included a language level variant specification as well. The next revision of the paper will tackle pattern matching separate from language level variants, and for which I'll be a co-author. So look forward to that. Announcements will be made later on. I don't know what the plan is for that yet. So what's the purpose of this talk? From my experience in the community so far, I found that a lot of people actually aren't exposed to functional style pattern matching. And so I want to introduce and familiarize the idea within the community so that we can actually have a conversation where we actually know what we're talking about when we talk to each other. Secondly, I'm seeking to find out some answers to some questions. First one is, why now? Why do we care now? What's changed? Right, it's been 30-something years. Why do we need pattern matching now? And the other thing is, can a modern library solution be good enough? We've been adding more and more language features, and we're getting more power to be able to write more powerful libraries. Can we actually have pattern matching in library form available? And we have a bunch of facilities that are considered good enough, right? Tuple, variant, pair, not good enough to everyone, but by the community, there's not been enough pushback against having library solutions, and it seems to be working okay for us. So On the other hand, there are also libraries such as Boost Lambda, which warranted a language level feature because it just wasn't going to fly. And lastly, if a modern library, if we deem a library solution to be not sufficient, then at least we can gain experience from having built one to guide the language design. At least for me, so that I can guide the language design. So this is the overview of the talk. We're going to have one slide on algebraic data types. I'm going to try to explain what pattern matching is at a more fundamental level and what it's trying to achieve. We're going to see various forms of pattern matching, very restricted forms of pattern matching that you see and use in C++ today. Then I'll introduce my library. We'll go through some examples, and I'll show some interesting features that I can't leave out because they're so interesting to me. But I think you'll find them interesting as well. So algebraic data types. It comes in two forms. The first one is a product type. So when we say a product type, we're talking about a data type that can be composed of multiple data types, and they hold an instance of both, or how many ever types you throw at it, right? So examples are like a tuple, where you can say tuple of xy, and it's going to store an instance of x and y. And the name product comes from the fact that we're counting the number of possible states of these types. And so for a product type, the number of possible states for a tuple xy can be in is the number of states that x can be in times the number of states that y can be in. On the other axis, we have some types where we can have one of the types that we gave it. So an example of this is a variant xy. It's going to store an x or y, and it's not going to store both. Okay, and we'll start with a claim. My claim here is that pattern matching is the best tool for decomposing algebraic data types. And we'll see examples and back it up. So what is pattern matching? This is a quote from Haskell Wikibooks. It says, in pattern matching, we attempt to match values against patterns, and if so desired, bind variables to successful matches. Here's a trivial example from Rust, written in Rust. We declare a point class with fields x and y. We declare a variable of type point with values 0 and 7 and 0. We're going to match on the p, and we're going to provide the cases that we want to match in order. So the Rust is actually going to check these cases in order, and in this case, it's going to fall into the second case because the y is 0, and we're going to print x-axis is 7. Pretty simple. Everyone follow? Good. I see nods. So a traditional way in which we would write this in C++ might look something like this, right? We can say we can manually go and check the individual fields and do the correct thing. So what's the difference? Well, pattern matching is a declarative approach in lieu of manually testing for a value with sequence of conditionals and extracting the desired components. Right? So the color coding here, I'm trying to emphasize that the patterns that were pink before is a sequence of conditionals now, and it's a declarative way of describing your conditionals. So we have a more elaborate example here, which is to evaluate expressions. So this is an expression tree. We have the expr, basically a variant here, which is going to store one of int, negative, add, or multiply. The box is basically a pointer because it's going to be a recursive type, and we'll have to do this in C++ as well, as we will see. So this is one way to write our eval function. We can take an instance of expr, match on the expr, and provide our cases. We can say if it's an int, bind the value inside the int to value, and then I'm going to return that. For negative, recursively call eval, and negative, negate it, add, multiply. Right? Evaluate both sides, do the right thing. Pretty simple. And you can see that on this axis, vertically, we're matching sum types, the alternatives of the sum type. And horizontally, we're decomposing a product type. Right, so we have a bunch of values, and we're going to decompose that into fields that and give it names that we want to refer to use it in the right-hand side. And note that patterns are composable. So here we have one layer of pattern, which is the sum type pattern, and then within the sum type pattern, we're going to decompose the product type into their names. So that's two layers of nesting. So this is the analogous example in C++. I'm going to use a shared pointer here. You might have noticed that. That's just for me to cheat later on. You'll see how I cheat later. I'm not going to hide the fact that I'm cheating here. Okay, so this is one way in which you might write your eval function. You check for every case that you have with the dynamic cast and rely on the implicit conversion and the fact that dynamic cast is going to return null pointer if it's not actually the thing that you asked for. And the challenge here for the programmer is that the if statement is a very flexible language construct, right? The operation that we're trying to perform is actually quite structured. And we're trying to use an overly general language feature to solve this particular problem and trying to get it and relying on the programmer to get it right. And oftentimes we don't get it right. And it's often the source of bugs. And it's also very unlikely for there to be a warning if and when there's a missing case, mainly because the hierarchy is open, but also because the cases are spread out as different predicates in an if statement. It's really hard for compilers to be able to reason across and actually tell you that you're doing something wrong when you're using something this general. And all right, you might say, oh, come on, MPark, no one's going to write this code in practice. Who would actually write this? I would use visitors or something. And all right, so here I'm just illustrating that we're testing manually with a sequence of conditionals what we want, and then this is our imperative approach. Okay, so yeah, no one would write this. This is code that I pulled out of LLVM. Din cast is faster, but it's essentially dynamic cast. If it's not storing the thing that you asked for, it's going to give you a null pointer. And this is all over LLVM. Not to say that that's bad per se. LLVM is a high-quality C++ project. But this is something that's pretty difficult to maintain, in my opinion. You might say visitor's better. Well, that's a lot of code. Compared to what we had before, we have this weird returning values idiom. Yeah, I don't want to do that. Okay, so a little insight from Swift. While I was doing research for this talk, I found this quote that I thought was insightful. And it said, this was from the document which was used during the design phase of introducing pattern matching to Swift. And it said, pattern matching was probably a foregone conclusion, but I wanted to spell out that having ADTs in the language, algebraic data types, is really what really forces our hand because the alternatives are so bad. And we just took a look at the two alternatives that that were so bad. And I think that this answers my first question, which was why now, and why do we care? What changed, right? The support for algebraic data types in C++ is pretty new. Right? We had tuple introduced in C++ 11, and variant only came in C++ 17. Before that, we had structs, which we couldn't decompose in any reasonable way, aside from actually naming the fields. And we had class hierarchies, which we didn't look at as a sum type. We kind of came from the object-oriented side of it and didn't consider them to be part of the algebraic data type family. So I think that answers my question for why we want it now. Okay, various forms of pattern matching you may have seen in the wild in C++. Let's start with simple types, and we'll talk about how product types and sum types are matched in C++ today. So matching simple types is pretty common, right? We use switches all over the place to match integrals. In this case, I just have an integer x, and I'm going to use a switch to perform some actions. And of course, someone will come along and say, why can't I match a string? And you'll be like, well, it only works for integrals. Efficiency? But if it's actually what you want, you should be able to do it, I think. So here's an alternative way to do it. This is Python-style switch, right? You can construct your own map, and then you can index into it and call whatever action you want to call. Two ways of doing it. Here's what it looks like to decompose product types. So to set it up, let's have pair x, y called P, and we'll have a tuple of pair x, y, and z. Cool. In C++17, we have still apply, which will allow you to unpack a tuple or pair or any tuple-like type, and we can decompose that into arguments into a function. Right, so we can say apply of this lambda, which takes x and y, give it a p, and it's going to expand the p into function as the arguments. On the right-hand side, I'm showing what it looks like if you had nested destructuring. It's not pretty. You have to apply the first level with t, and then you have to expand again with the second layer. And you're going to have, let's suppose you have 4 layers of expansion that you want to do. You're going to be going in, depending on how many spaces you indent with. If you indent with 2, let's say 4 levels, you're at 8, 10 that deep, right? There's also a new way to do it. C++17 introduce structured bindings. We can now say auto xy equals p, and we're going to expand the p into the variables x and y. On the right-hand side, I'm trying to show how t would be decomposed. The last line is something that you might think that is possible intuitively, but this is actually not supported. And so, again, we have multiple levels of nesting when we try to actually decompose complex data types. So let's change the hierarchy a little bit and use a variant so that we can visit it easily rather than having to do the whole setting up of the visitor hierarchy. And the code looks more or less the same, except we're using std_visit now. And again, I'll point out that if you were to nest your classes, your types, for example, if you wanted to reach into neg in the negation case and look into visit the expr inside the negation, then we're going to have to do another layer of visitation, which is nested inside. Okay, this brings us to my library. So I have 4 goals for the library. One is that I want this to be declarative. I would like to avoid having to spell out the state that I'm looking for. I want to just describe what I want and then see if it matches. Number 2, I want it to be structured. The chain of it, as we discussed, the chain of if-else's are overly general for the task at hand. Cohesiveness. The reason why I showed I think it was 7 or 8 different ways in which we can decompose algebraic data types in C++, right? We just went through three tasks, and each of them had 2 solutions, at least 2 solutions. So the various forms of pattern matching we explored are very hodgepodge, unsatisfying solutions to pretty simple tasks at hand. And each of them had their own limitations, switches with their integrals, visitation with their difficulty to nest, as well as structured bindings. Even the newest stuff has limitations that we're not all that happy with. And most importantly, it needs to be composable. And the reason why patterns must be composable is because ADTs are composable. Because algebraic data types, because we build values out of smaller components and we build on top of each other, we need to be able to do the same thing with patterns to be able to reduce our cognitive overhead. So this syntactically, this is what it looks like. This is the basic structure. All of the, you can just include MPark/patterns.hpp. The using namespace is going to pull in all the necessary components. You can match on multiple expressions and then provide multiple patterns, provide your bindings, and it's going to execute them in order. In order. First fit execution. Okay, so let's get back to the point example. We had point xy. We're going to instantiate, create an instance of point with 7, 0, and we're going to say match p, and we're going to provide the ds pattern. This is the destructuring pattern. And we're going to say the first one needs to be 0 or anything. The second one's going to be anything or 0. The last one can be anything, anything. And you can see the variable bindings being introduced as the function parameters of the lambda on the right-hand side. So arg is the binding pattern, and it's going to match any value and pass that value onto the handler on the right-hand side. And if there are multiple args, it's going to pass them over in the order in which they appear in the pattern. Pretty clear? And getting back to the evaluating expressions example, we now specialize variant size here. And this is to communicate to the library that I am a variant-like concept, that I modeled a variant-like concept. So just a side note, if you're using structured bindings and you, for example, say, introduce a struct that inherits from a tuple, and you try to use structured binding on that, that will give you an error because of this exact issue. It's going to think that your type doesn't model tuple-like because you didn't specialize tuple size. So tuple size and variant size are the customization points for which you communicate to the language feature or my library that you are tuple-like or variant-like. Okay, so this the evaluation might look like this. We match on the expr, and the as pattern is a new pattern, and this is going to be the pattern that matches polymorphic types, variant-like types, and any like types. By any, I mean the std any that was introduced in C++17. So you could throw whatever into an any and get stuff out with an any cast. With this pattern, you could get stuff out of an any cast. You can get stuff out of an any by the library executing the any cast operation. So here we have a variant, or at least something that we opted into as a variant-like type, and we're going to provide our alternatives, and we're going to also provide the nested pattern here. We already saw the ds pattern, which was the destructuring pattern, and that appears within the as pattern. And we're going to bind the desired parts onto the right-hand side. Here's another example. Here I have an optional flag example. Suppose we have an optional command line flag, and we're going to analyze the input. So we match on the flag, and the first one, and so the new patterns here are some, none, any of, and a different use of arg. So let's go through it. So some is a pattern that the syntax would be sum of some pattern inside. So I could say sum underscore, which, we could say sum arg, which would say if you're an optional and you have a value, then give me the value. You could say sum underscore, which is a wildcard, which I actually haven't introduced, but it's pretty intuitive. It just ignores any value that binds to it. And so if you say sum underscore, then it's going to match an optional if it has a value, but it's going to drop the value, for example. None will match if the optional is empty. Any of is typically seen as the pipe operator in functional languages. It's the alternation pattern. You can give it multiple patterns, and the whole thing will match if one of the patterns match. The use of arg here is basically, so what we're trying to do is we want to match the optional. If the optional is set, and the value is underscore v or under verbose, then we want to dispatch to this case. Now, once we get into the case, how do we know which one matched? Right? We don't know whether it matched because it was an under v or because it was an under dash dash verbose. So by wrapping the arg around the pattern that matches the value, it'll pass the entire value that matched at that level onto the handler. So on the right hand side, we get the string that matched, and it'll have to be dash v or dash dash verbose. The second one, in the second case, we introduce pattern guard. So the when clause there, that's bolded. So the sum arg, as I described, will match a optional that has a value and pass whatever value it's holding onto the handler. And the when guard will execute, and we will only execute the handler if the when guard succeeds. So if the when guard fails, the difference between when and an if would be that an if, you would still stay within that handler, whereas if a when fails, you fall through to the next case. Does that make sense? Nods? Good. Okay? All right, so summary of the patterns that I've introduced so far. We have expression pattern. So the expression pattern we saw in the first example when we were matching 0, right? We saw arg and wildcard. Yeah, we saw wildcard. Did we? Okay, oh yeah, I introduced it. Okay, cool. So the destructure pattern we saw first, and the destructure pattern operates off of a concept as well. And the concept is an array, and when I say array, I mean a C array, an aggregate or a tuple-like. And by tuple-like, I mean the tuple size, tuple element, and get interface that structured binding uses. So this is really useful, and that's why our initial point example worked without any boilerplate of introducing tuple size and get and stuff like that. So the as pattern, as I mentioned, matches some types, polymorphic types, variant-like types, any like. Optional matches pointer-like types. So the example that I showed was with a std optional, but you could also match pointers with it, for example. And alternation, yeah, it's going to match one of the n patterns and then dispatch to the handler if any of them matches. Okay, let me take a sip of water here. This is our big example. Okay, so what we're going to do is take the expression tree that we've been working with, the latest one that we saw with the variant, and we're going to simplify the expression tree. And the simplification rules that we'll cover are double negation, plus 0, multiplied by 1, and what's the last one? Multiplied by 0. And we want to keep the original tree intact, and we want to share as many nodes as possible. Okay, so just a review, just a refresher on the expression tree that we've been looking at. Nothing's changed. So the first case, we'll go through it case by case. So the first one is a simple case where we're just simplifying an int. We take some expression tree, we match the expression, and if it holds an int, we don't even care what it holds. We're just going to return the expression directly. So if that's the expression, our result is going to be just another shared pointer that points to the same integer. Here's the double negation case. So just a reminder on the colors. The purple is the value that we're matching. The pink is the patterns that we're matching with. The yellow is the variables that we're introducing. And the green represents the tree. So the double negative case, so we're going to first match the outer layer with a negation node. Within that, we're going to destructure the negation node into its part, which it only has an expression. We're going to then, because it's a pointer, we're going to access the value inside the pointer, which is the expression, with the sum. we then match another negation node. Right? So if any of these fail, so for example, if the shared pointer is null, which in our case it can't be, it would actually not match this pattern at all. Right? So we're not running into some null pointer exceptions or anything like that, or no, it's like dereferencing null pointers or anything like that. And then when we get to the part that we want, we're going to dispatch bind the value that we actually want, and we're going to simplify that, and that's going to be our result. Right? We're going to recursively simplify, throwing out the two negations. We're going to simplify the expression that stands two levels deep. So this is our result. Right? We simplified the minus 17 to just 17. Go through the rest of it a little bit faster, perhaps. Here's plus 0. Now we have two cases. We're going to match 0 of anything and anything with 0. So we have the as pattern again, match the add. We're going to destructure that add, which has two components. And so the left-hand side, we're going to say if that thing actually holds a 0, right? We're going add int, and also checking that value is 0. On the right-hand side, we don't care, and then we're going to throw out the 0 and simplify the other side. So in this case, we have expr left and right, and our result is going to be just 17. Multiplied by 1, it looks exactly the same, except we change multiplication, change it to multiplication and 1. Same case. So we'll just skip over that. The multiply by 0 case is pretty interesting. So similar pattern, right? We have a multiplication. And we're going to inspect both sides, 0 or anything or 0, and we don't care what the anything is, because we're going to return 0. But remember one of the requirements that I mentioned at the beginning of this exercise, which is that we want to share as many nodes as possible. So what that means is when we want to return 0 here, but we don't want to create another node for 0. We want to actually reuse the 0 that's already there. And so this is where I use the arg pattern that binds a bigger portion of the pattern that you wanted. So here I'm actually saying, look down and see if there's a 0, and if there is one, give me the entire shared pointer so that I can copy that, right? Because otherwise, I don't have access to the actual the pointer to 0. So in this case, I'm going to actually get the result to be 0, and it's not going to be a new 0; it's going to be an existing one. Simplifying negative in general. So when it's not a double negative, then we're going to, the case is actually pretty simple. So we're going to first try to simplify the thing underneath the negative. And if that changes anything, then if it doesn't change, then we're just going to return the result. So basically the first case here, the first case in the conditional is the left-hand side diagram. And we try to simplify E, and the simple E comes out to be, oh, it's the same thing. Okay, well, if it's the same thing and you can simplify it, then just return the thing that you had before. If you try to simplify and you don't get the same thing as E, so here we have the simple E at 17 as opposed to E, which is pointing at the plus. Right? So if it's not the same, then what that means is that we were actually able to simplify some stuff. And so we need to make a new node, reattach it, and then this is our result now. And this is because we want to, the first requirement, which was that we want to keep the original tree intact. Right? We don't want to modify the top level minus to point at 17. We want to actually keep that one intact and leave it alone. Looks more complicated, but it's exactly the same thing. We simplify left-hand side, simplify the right-hand side, and we check whether anything changed. If nothing changed, then we return the result. If something changed, in this case, for example, then we're going to create a new node, reattach, and return the result. And multiplication here is exactly the same thing. So if it didn't change, return the tree. If something changed, create a new node, reattached, return the result. And putting it all together, I've consolidated a bunch of the cases with any of, which was the alternation pattern. And so you can see that if it's negative, negative, negative v plus 0, or v multiplied by 1, all of them, we just ignore the thing and simplify the expression. If in the 0 case, it's a little different, where we bind a sub portion of the value, and we saw some of the more complex cases in the generic cases. So what I'm trying to highlight with this example is the nesting, right? Maybe that's obvious, maybe that's not, but I would like to point it out explicitly because that's really the power of pattern matching, which is to describe the full state of the value that you're looking for, and we just see if it's there. And this is basically what I just said. The real power of pattern matching is that the patterns are built the same way as values. I want to show you a few more things. These are some of the challenges that I ran into and some of the cool things I found. So one of the challenges is the identifiers, right? Introducing identifiers. There's only so many contexts and so many ways and you can introduce identifiers in C++. And in functional languages like Rust that we saw, well, Rust isn't a functional language per se, but they allow you to introduce identifiers within the pattern. Right, so when we said point xy, we're introducing new identifiers in place, and we can use that on the right-hand side. We don't have that luxury in C++. I can't just introduce identifiers within an expression, and so my current solution is to say, all right, let me just fill it in with placeholders called args here, and then actually give it the name on the lambdas on the right-hand side. But from the examples, based on the examples you saw, you can see that it's actually very verbose and difficult to read because when you look at the pattern, you just see a sequence of args, right? Arg, 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 arg. Like, okay, what's that, right? If the fields actually have some meaning and you were able to give them names, they would actually be a lot better. So patterns do not have any identifiers. So can I do something about this? And before we get to whether we can do anything about it, this is you saw an example of pattern guard before. Simple example of Fibonacci where if the value is less than or equal to 0, then we're just going to return 0. And the reason why this when is inside the lambda and not closer to the pattern, which is what most of you would probably expect, is for the when to be right next to the pattern, right? Because that's the whole criteria for which you need to satisfy before the handler gets called. But this when is inside the lambda because if I were to pull the when out and put it beside the pattern, then I need another way to introduce identifiers. And this way, I'm actually leveraging the fact that I already introduced an identifier with the lambda, and I want to just be able to refer to that and use it immediately. It's inside because we want to reuse the identifier. So this is another experiment that I've conducted, and I actually quite like it, but I haven't fleshed it out fully yet. But I still think it's pretty cool. So you can introduce identifiers before the entire thing. So it's a little unfortunate that you have to be, you have to list off all the identifiers you're ever going to use in all the patterns up front. But it's really in the lambdas or before the expressions. So this is the only other place that I was able to find something. Okay, and we can let me go back. And we can use the identifiers that we introduced, x and y, inside the pattern. And so, for example, if you had more meaningful names, it would be helpful inside a pattern because you no longer just see arg, arg, arg. Maybe you see first name, comma, last name. Right. So the cool part here, So the identifiers, it's all in caps, which means?
It's a macro.
It's a macro. Why is it a macro? If it's just the arg, why couldn't we have just decal type arg and then just gave it names? And the fancy thing here is that repeated identifiers mean the values have to be equal. And I find this really cool because most functional languages actually don't support this. And it's interesting because I think the reason why they do it is related to the fact that they're introducing identifiers in place. Right? They're introducing identifiers in place, and they're saying, well, you introduce another identifier, you have a duplicate identifier essentially, right? As opposed to saying, okay, you said this thing again, and we'll take that to mean that you want it to be the same value as the first one that you declared, right? Same reason why we can't declare multiple variables of the same name in C++. Whereas if I declare it up front, when I refer to it twice, it's pretty clear that I'm referring to the one that I already introduced previously. So here's a kind of a dumb example, but we have a triple, 101, 202, 101, and I can provide my patterns XXX or XYX, and it's going to do what you expect. Good? I find it fun. Back to the pattern guard. Because I've taken on this burden of having to introduce identifiers beforehand, I should be able to use it, right? Somehow. So this is a way in which you can create lambdas in place, similar to how Boost Phoenix would do it, where you have some magic placeholder, you perform some operations on it, and I'm going to hijack those operators and create a lambda for you. And so this is implemented and works. I don't know about the EDSL approach. I don't know which one I hate more, basically. The when macro inside the lambda is, the distance is a bit far and macro. And this one's, it's kind of nice, but DSLs. So, midst of experimenting. This is the cool thing that I found that I wanted to show you. Variadic pattern. Another thing that a lot of functional languages don't have. But a lot of functional languages also don't have variadic templates. So that's, I think, where the difference is. So this pattern can appear exactly once inside of a DS pattern, the destructure pattern. And it's going to repeat itself how many ever times it likes, how many ever times it needs to. So it could even appear as the first argument in a destructure pattern, and it's going to expand itself how many ever times it needs to. So here's a quick example, another triple, and we're going to say decompose it into three parts, or I could also say variadic arg. And it's actually not any shorter, so that's unfortunate. Where it gets interesting, though, is when we throw it inside of a template. So we create a template here, we have some tuple, and with the arg, arg approach, well, we would have had to somehow get the tuple size, expand that into an index sequence, and then have the arg expand out that many times. This way, we can actually just say variadic arg, and that will actually just expand how many times it needs to, based on the tuple that comes in, that it gets instantiated with. Pretty cool. What does it look? It looks kind of familiar. This is actually C++ 17 apply. Right? We can take some function, a tuple, we match on that tuple, we're going to expand it, and our handler is just the function that we're calling. Right? Cute. We can get a little fancier though. We have, this is almost tuplecat. The almost part, we'll see if anyone sees why. So we have another triple. This is just showing that, remember, we can expand the tuple with ds variadic arg. So if we can expand a single tuple with ds variadic arg, then if we have n tuples, how do we expand all of that? We would have ds variadic arg comma, ds variadic arg, comma, ds variadic arg, comma, dot, 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 right? So, okay, that looks similar. So we'll have variadic, ds variadic arg. We'll take how many ever tuples we get, expand all of that. The arg is going to expand how many ever times it needs to. They dispatch to the handler in order of how they appeared. And it only appears once, but once it's expanded, if they appear multiple times in order. So we pass all of those along, create a tuple. Where is the almost? It looked fine to me. But TupleCat does this weird thing where if you take tuple of x's catted by tuple of y's, it'll always give you tuple of x's and y's. Whereas here, if I have tuples that have references in it, for example, this will always create values. Right? It's going to decay all the elements and decay construct values out of those references. So it doesn't exactly do TupleCat, but hey, it's still pretty cool. People might be concerned about performance. So to be honest, I don't care about performance. And what I mean by that is for this particular project. And that's because the open pattern matching for C++ that Yuri, Gabby, and Bjarne did has a lot of research as to how we can actually get performance out of these constructs. So what I'm mainly focused on is how do we introduce identifiers and where, and how do we actually get this API to be usable? Because if you actually compare the library examples to some of the examples you'll find in functional programming, it's actually very verbose. So I'm more focused on how to get focus on getting the API clean and experimenting with what kind of patterns are out there, what kind of problems exist specifically for C++. But I did this experiment because I was curious. So I went on Godbolt, plugged this in. This is a simple implementation of FizzBuzz where I iterate through 1 to 100. I'm going to mod 3, mod 5, do the multiple values match 0, 0, FizzBuzz, 0, 0, anything, buzz, anything, oh, fizz, anything, 0, buzz, and anything, print the number. And here's how I would written it, the same program in regular C++, like basically the fastest way I know how to write it, while maintaining the same semantics as the previous program. And they both compile down to this exact sequence of assembly. They generate the exact same code. There are other examples that don't, but this one does. And I think this is more so credit to the compilers, not to me, because I actually didn't do anything to make it performant. So kudos to compiler vendors. And that's actually true for Clang and GCC. So some future work. So what I haven't shown you that you typically expect from a pattern matching mechanism is expanding lists, ranges. The difficulty there is that for functional languages, lists are recursive. They're essentially just pairs of pairs of pairs, right? You just const them onto each other and you break them up into 2 parts. Whereas for us, they're actually ranges which have begin and end. And that's fundamentally a different way to represent lists. And so for example, if I match a vector, how do I break that apart? I can say arg to pull out the first element, and then how do I describe rest? Right? I need to describe somehow the notion of tail. We don't really have a good mechanism to describe tail in a range. Maybe Eric's range library will help. Experiment further with identifiers. The current state, it's okay, but it's not great. And lastly, exhausting checking. I haven't done any work there, but it would be really interesting to find out what we can do there. So that's all I have. I think we have 10 minutes left for questions. If if we don't have any questions, I have some more stuff. All right, any questions? Yeah.
What's the status of the TS?
Well, there is no TS. So the question is, what's the status of the TS? The answer is that there is no TS. There was a proposal that was written, but I don't think was discussed at the committee meetings. We'll see what the next iteration of that paper.
What about the language
Which
variant?
proposal do you mean?
Sorry?
Sorry, the language variant.
The language variant one? Oh, yeah, that's what I'm talking about. So yeah, so that paper, I'm not sure if it was discussed.
You mean David's paper?
Yeah.
From last year, it was discussed in August.
Okay, and was there any news about that?
There was discussion.
There were there was so.
I think we're waiting on him to come back with the revision. I don't remember.
Yeah, I think the main takeaway was to split the paper into multiple.
Yep. Right. Okay. So the question was, what's the status of the paper that was written? The one that I mentioned at the beginning of the talk. The status of it is that it was discussed in Ulu, and we're waiting for the next iteration, for which I'm a co-author. So I guess some of that's on me to deliver. Yeah, Jason.
So you're talking about introducing identifiers,
Yeah.
but in a more general sense, you're introducing free variables, right? Because you're introducing the idea
Yes.
that they actually represent the same value,
Right.
right? Because of the automatic equivalency checking, right? So,
Mm-hmm.
so what's missing is type, right? It's not just X, it's the free integer X or the free string X or whatever, right? So, and you might auto that. So
Mhm.
you don't really care what the type is.
Right.
But you might not, right? Because we might specifically want to constrain that way. My pattern will match X that's an integer.
Right.
So I think maybe you may have actually sort of just stuck your spade directly into why this has to be a language feature. You're introducing not an identifier, but a variable.
Okay, so let me try to summarize that. So Jason's comment was that when I talk about introducing identifiers, what we're really talking about is introducing free variables for which we're trying to resolve its value, and there might be type constraints that we want to put on them and stuff like that. In conclusion, he thinks that I may have hit on the reason why it needs to be a language feature. Yeah, maybe. I don't know. But the only comment that I have is the comment about constraining types. Like, oh, I want this pattern to be an int. Right now in the library, I actually get some of that with this type checking. Right? Like if the rest of the values are integers, like you can't. The type system won't let you put anything else there. And so for example, if I have a 3 tuple and I try to match that with a pattern ds underscore underscore, that's not gonna compile. It's not gonna just ignore it and continue. It's just not gonna compile. And so in some sense, the type system helps me with some of the exhaustiveness checking, right? In the sense that we have patterns that are never gonna match because the types don't match, and I'm not gonna execute those because, well, I'm gonna tell you and not compile because I know this is never gonna work, never gonna run. So it's kind of, yeah. It's kind of interesting.
In some case, right, it's very similar to the visitor for parent.
Mm-hmm.
If we can disambiguate on the type,
Yeah.
then it's the same. It's a type switch now.
Yes. Right. Yeah. Yeah. So the comment was that the visitor or the as pattern introduces types and the alternatives, and that's very similar to visitor, and that's just it's essentially a type switch. And if we can do exhaustiveness checking on that, then we can. It'll be very useful. Any other questions? Okay, if there are no questions, I have 5 minutes if you guys want to see a peek of the implementation.
Yeah.
All right. So this is the structure as I described earlier. So the pattern here is going to generate or give return a value of this prop C intermediate class, which has an operator equals, which returns something that it probably shouldn't be returning. It's not pattern ref. We're returning some completely different type. So we're returning some case, and this case comes from this equals here. So considering that whole thing, we return this whole case, and the match is going to return this intermediate type, which is an operator paren, which is how we are able to actually make that second set of paren calls. And it's going to take a sequence of cases. And it's going to store the values. And once we actually call the operator paren, then we're going to try each of the cases in turn. So the try match function there is the customization point to introduce new patterns. So, did I hear something?
Sorry, I'm just realizing that this is where we could do best match instead of first match.
This is where we can do best match instead of first match.
You have to pass over and score them first.
Pass over the what first, sorry?
You have to pass over the cases and score them first and then do best match.
Right, yeah. So, yes, and this is where I would do exhaustiveness checking as well. So the reason why I'm not so why I'm optimistic about exhaustiveness checking and stuff like that is because I know I have all the information in place, right? It's not like, oh, I don't know if I'm actually going to have enough information to be able to do it. Like, I know I have it. I just need to read papers to figure out how to do exhaustiveness checking, and then we'll figure it out. Best match, I think, is something that I don't really want to do. If you look at, so we have a lot of pattern matching mechanisms in C++, namely like overload resolution, for example, is a best match, best fit pattern matching. And overload resolution rules are so complicated because we're trying to figure out which one is best as opposed to just saying, oh yeah, this one's fine, right? This one's matches. And so we have all these rules around integral conversion sequences, and I think the complexity that it adds, I mean, it's nice, but I'm not sure if it's worth it. Okay, let's move on. Okay, hold on. So first of all, this would have been two functions if it weren't for if const expr. And I'm using if const expr like all over the library. I think yes. So last night I counted, and I have 48 instances of if const expr in the library right now, which is my new favorite language feature. So what is this result here? This result has type match result. And it returns it inherits from optional forwarder, and the forwarder thing is there because optional doesn't let you put references in it. And when I call the function, it might actually give me references, and I actually need to forward that reference out properly. So that's why that's there. We're not going to look at forwarder. It just forwards stuff through. It's not all that interesting, but it's tricky to get right. So here's match result aware invoke. So if you call regular invoke, then you're going to have to deal with void and stuff like that, right? Because Matt hasn't finished his paper.
The paper's done.
The paper's done. Matt is trying to push regular void through C++. Hasn't happened yet. So for now, I have to deal with this stuff. Is void. If it's void, then create the void type and make sure you propagate the void properly. And if it's a match result, don't layer match results on top of each other, etc. And this function is what the try match function uses. So here's the implementation of try match for expert pattern, and the expert pattern is like it's just a name, right? It's gonna take any value and just compare equality comparison. So we take some value, we perform an equality comparison with the value that we're trying to match, and the third argument there is the function that you give all of the values that you want to pass to the handler to that function. So in this case, an expression pattern doesn't match anything, so it's going to just call f with nothing. Whereas the arg pattern, which actually passes the value over, is going to, if you look at the invocation for match invoke, is going to pass that value over to the handler. And if the arg has if it's the more sophisticated form of arg where it has a nested pattern, then we're going to just delegate that to the inner pattern. Make sense? That's it. This is not for you to see. Thank you everyone for coming. It was fun.